You see it every single day, right? The world around us is constantly changing. Water freezes into ice, a sliced apple turns brown. I mean, it's everywhere. But have you ever stopped to think about what's really going on? What's the science behind it all? Well, let's get into it.
Okay, so just think about this for a second. When ice melts, you still have water, right? You can just freeze it again. But when you bake a cake, there's no way you're turning that back into eggs, flour, and sugar. So are these changes actually the same? Well, the short answer, absolutely not. And figuring out why is key to understanding, well, pretty much everything.
All right, so let's dive right in and break this down. We can basically sort every change you see into two big categories. It's either a physical change or a chemical change. And knowing the difference is why you can refreeze an ice cube, but you can't unburn a piece of toast.
So first up, we've got physical changes. Think of it like getting a haircut. You might look different, but you're still you, right? The same goes for matter. When you tear a piece of paper or melt an ice cube, you're not actually creating anything new. You're just changing its shape or its state. It's still paper, it's still water.
But a chemical change, well, that's a whole different ballgame. It is a total transformation. When you burn a log in a fireplace, it turns into ash, smoke, and gas. You can't get that log back. Or when a nail rusts, it's not just iron anymore. It's become a brand new substance called iron oxide. The original stuff is literally gone.
And this table here, it lays it all out perfectly. Look. With a physical change, no new substance is formed, so it's usually temporary and easy to reverse. But with a chemical change, you get something totally new, which means the change is pretty much permanent and really hard, if not impossible, to undo. And this idea of permanence, this is a fantastic way to think about it. You can't unscramble an egg, right? And you definitely can't take the black ash from a burnt pan and turn it back into the butter and egg you started with. A new substance has been formed, and that's a one-way street.
Okay, so how can you tell a chemical change is happening right in front of your eyes? You gotta be a detective. Look for the clues. Is there a sudden change in color, like an apple turning brown? Do you see bubbles or fizzing? Does it suddenly get hot or cold all by itself? These are all telltale signs that a chemical reaction is underway.
All right, so we've got a handle on what a chemical change is. But now, things get even more interesting. Because not all of them happen at the same speed. Not even close. Some are incredibly slow, while others are, well, explosive. This brings us to the speed of change.
I mean, just look at the massive range here. On one end of the spectrum, you have the rusting of iron, which can take years. In the middle, you've got something you can see in minutes, like that apple browning on your counter. And then, all the way on the other end, you have an explosion, a chemical reaction that's over in a fraction of a second.
And this leads us to a really good question. Rusting is a chemical change. An explosion is a chemical change. So why is one mind-numbingly slow and the other terrifyingly fast? What's going on under the hood that controls the speed of these reactions?
Well, the answer, it turns out, lies in this really cool concept called the collision theory. And you can think of it as the secret recipe, the fundamental set of rules that determines if a reaction will happen, and if so, how fast it's going to go.
But before we get into that, let's just get a quick definition out of the way. When scientists talk about the rate of reaction, it's just a fancy way of saying speed. It's all about how fast your starting ingredients, the reactants, turn into your final result, the products.
Okay, so here's the deal, the big idea behind the whole theory. For any chemical reaction to happen, two things absolutely have to be true. First, the little particles of your reactants have to physically crash into each other. No collision, no reaction. Simple as that. But, and this is the important part, just bumping into each other isn't enough. The collision has to be powerful. It needs enough energy to break the old chemical bonds so that new ones can form. And that minimum amount of energy needed, that's called the activation energy.
Now, this is where it gets really cool. Because once you understand this theory, you realize we can actually control the speed of reactions. It's not just random. We have a whole toolkit of things we can tweak to either speed a reaction up or slow it way down.
And here are the 5 main tools in our toolkit. To change how fast a reaction happens, we can play with concentration, pressure, surface area, temperature, and something called a catalyst. Let's take a quick look at each one.
First up, concentration. And this one's pretty easy to wrap your head around. If you pack more particles into the same amount of space, what's going to happen? They're going to bump into each other a lot more often. More collisions means a faster reaction.
It's like being in a crowded room versus an empty one. You're just more likely to bump into someone.
Now for gases, pressure is kind of like the cousin of concentration. When you crank up the pressure, you're basically squishing all those gas particles closer together. And just like with concentration, when they're more crowded, they collide more frequently. And bingo, the reaction speeds up.
Oh, this one is a great example, and you see it all the time in the kitchen. A big whole chicken takes forever to cook, right? But if you cut it up into little pieces, it cooks super fast. That's because you've massively increased the surface area that the heat can get to. It's the exact same idea in chemistry. Grinding a solid into a fine powder exposes way more particles, which means way more collisions can happen at once, and the reaction just takes off.
And then there's temperature, which is a real heavy hitter. It actually gives you a 2-for-1 punch. When you heat things up, the particles get more energy. So first, they start zipping around way faster, meaning they collide more often. And second, when they do collide, they hit with a lot more force. This means more of those collisions are going to have enough energy to get over that activation energy barrier we talked about.
And last but not least, we have catalysts. These things are like chemical matchmakers. A catalyst is a substance that makes a reaction happen faster, but, and here's the cool part, it doesn't get used up in the process. It's a helper. And it works its magic by creating an easier path for the reaction, basically lowering that activation energy bar. Your body's filled with them, by the way. We call them enzymes.
And I love this analogy. It's the perfect way to picture how a catalyst works. Imagine a reaction is like a car that needs to get over a giant mountain. That's the activation energy. It's a lot of work. A catalyst doesn't push the car harder up the mountain. No, instead, it builds a tunnel straight through it. It provides an easier, alternative route that requires way less energy, so the car can get to the other side much, much faster.
And there you have it. From the fundamental difference between melting ice and baking a cake, all the way to the 5 tools you can use to control the speed of a reaction. Now you know why you put food in the fridge to slow down spoiling, or why a sugar cube dissolves faster in hot coffee. So the real question is, after all this, what everyday change are you going to look at a little differently now?